the direction of the magnetic flux lines can be detected by the direction of a north pole of, yes, the magnetic needle of a compass. And now talking about magnetic field due to, yes, a current in a straight wire. Okay, talking about a straight wire. Current carrying a straight wire and the field produced by this current. Okay, as you see, the lines of the field are a series of concentric circles. Concentrics mean they have a common center. So the lines are a series of concentric circles with their common center at the wire. So the wire acts at the center of these, yes, circles. Okay, the plane of the field lines, what about this plane, is perpendicular to the wire. It is shown in front of you. The field, the plane of the field lines is perpendicular to the wire. The direction of the field is practically determined by using a plotting compass. And what about theoretically? Okay, the direction of the field, practically direction of the field can be determined by using one of the following rules. Okay, this when we talk about theoretically. First rule here is Ampere's right hand rule. Okay, in front of you, it is shown in front of you. Imagine the wire to be grasped. Imagine the wire to be grasped in the right hand with the thumb pointing along the wire. So, thumb points in the direction of the current. And the direction of the fingers, curl of the fingers, will give the direction of the magnetic field. Okay, this was about the first theoretical rule used to determine the direction of the field produced by current carrying a straight wire. Also, we've got another rule, we call it Maxwell's corkscrew rule, or the right-hand corkscrew rule. What about it? Okay, imagine a corkscrew being screwed along the wire in the direction of the current. The direction of rotation of the screw gives the direction of the magnetic field. Okay. And now we've got something very important, a convention. We call it dot, the dot and the cross convention of the direction of the current. Okay. Your attention. X means, yes, we've got a wire through which a current is passed down into. Okay, so this, we call this X convention. X means when we talk about something and it is symboled by X, denoted by X, so it is directed down into the surface shown in front of you. Okay, if it is denoted by a dot, okay, dot means out of page. X means down into page. Okay, so remember these two conventions, very important. Note, the direction of the field depends on the direction of the current. What does it mean? If the direction of the current is reversed, yes, the direction of the field will be also reversed. Magnetic flux density beta at a point of normal distance d from the wire. What about the relation expression that determines the magnetic flux density at a normal distance from the wire? Okay, it is determined by the expression beta equals mu I over 2 pi d. I is the current intensity, d is the normal distance, and yes, mu is the permeability. So mu is the magnetic permeability of the medium separating the point and the wire, the medium surrounding the wire. When the medium is air, permeability equals 4 pi times 10 to the power of negative 7 vapor ampere negative 1 meter. It follows, okay, beta equals 4 pi times 10 power negative 7 I over 2 pi d. So we can say beta in this particular case, when the medium surrounding the wire is air, the formula used, the expression used, beta equals 2 times 10 to the power of negative 7 I over d. Total magnetic flux due to two wires carrying currents in the same direction. So we've got two straight wires carrying currents in the same direction, and we want to calculate total magnetic flux. Okay. In front of you, we've got two wires, wire A, or the first wire 1 and wire 2. They carry currents in the same direction. Your attention, please, in between the two wires, in the region in between the two wires, the flux lines are in opposite directions. But outside the two wires, the fields have the same direction. When the fields are in opposite direction, the formula used, B1 minus B2. When they are in the same direction, the formula used is B1 plus B2. Once again, between the two wires, the fields are in opposite direction. Outside, they have the same direction. So, between the two wires, the two fields are in opposite directions. So B total will be B1 minus B2 when B1 is greater than B2, or B total equals B2 minus B1 when B2 is greater than B1. This, yes, talking about the total field in between the two wires. Outside the two wires, the fields have the same direction. So B total is determined by the expression B1 plus B2. Total magnetic flux due to two wires carrying currents but in opposite directions. It is exactly the opposite, okay? Two wires in front of you carrying currents in opposite directions. The fields in between the two wires, yes, have the same direction. B total will be B1 plus B2. Outside, yes, they are in opposite directions. B total will be the difference between them. Okay, once again, between the two wires, total magnetic flux at a point between the two wires is determined from the formula B total equals B1 plus B2. And what about outside the two wires? B total will be B1 minus B2 when B1 is greater, or B2 minus B1 when B2 is greater than B1. Okay, and now we've got something very important. Okay, talking about how to locate, how to determine the position of the neutral point. What's meant by a neutral point? It is a point where the two fields are equal and opposite, so they cancel out, they cancel each other. Once again, locating the position of the neutral point. It is somewhere in between the two wires. When the two wires carry currents in the same direction. Okay. Here we've got two wires Okay, and they have currents in the same direction. The neutral point is somewhere between the two wires. Let it be at a distance x from one wire. Let it be at a distance x from the wire carrying current I1. So it must be at a distance d minus x from the other wire. Okay, so in front of you we've got two wires carrying currents in the same direction. The field between the two wires are in opposite direction. So we can find the neutral point somewhere in between. The distance between the two wires is denoted by d. Neutral point at a distance x from one wire, so it'll be at a distance d minus x from the other wire. Neutral means equal and opposite, so B1 equals B2. Okay, general formula, permeability I1 over 2 pi x equals, yes, mu I2 over 2 pi d minus x. Yes, there are things that will be crossed out, of course. So we can say I1 over x equals I2 over d minus x. Rearrangement, we can say I1 over I2 is equal to x over d minus x. This, when we've got a neutral point, yes, somewhere in between the two wires. This is the expression, the relation that should be used to determine, to locate the position of the neutral point. I1 over I2 equals x over d minus x. Also, neutral point, this is very important, always lies closer to the wire carrying the weaker current. Okay, bear this into your mind. The neutral point, okay, lies closer to the wire which carries the weaker current. Okay, neutral point will lie outside the two wires when they carry current in the opposite direction. And once again, it should be closer to the wire carrying the weaker current. And what about the formula used to determine the position in this particular case? Okay, in front of you we've got two wires carrying currents in opposite direction. Neutral point here, yes, lies, it is somewhere outside the two wires and closer to the wire carrying the weaker current. So I1 is, yes, is smaller than I2. It is less than I2. So the neutral point is at a distance x from I1, and it will be at a distance d plus x from the other wire. Once again, if current I1 is less than I2, so we can say B1 equals B2. So mu I1 over 2 pi x is equal to mu I2 over 2 pi between two brackets d plus x. Okay, so we can say I1 over x equals I2 over d plus x. Rearranging, I1 over I2 equals x over d plus x. And don't never forget the position of the neutral point will be outside the two wires, closer to the wire carrying the weaker current. And now talking about the factors affecting the magnetic flux density of the magnetic field of a current, yes, carrying a straight wire. What about the factors affecting the magnetic field produced by the wire? First of all, first factor is the current intensity, or the intensity of the current flowing through the wire. Second factor is the normal distance from the wire and the permeability of the medium surrounding the wire. Magnetic field due to a current in a circular coil. In front of you we've got a circular coil and the current flows in a clockwise direction. What about the shape of the field lines? The field lines run in loops from one face to another. So the field lines run in loops from one face of the coil to the other. The field is similar, this is very important, to the field produced by a short bar magnet. Field produced by a short bar magnet. And the coil acts as if it has, okay, a north pole on one face and an S pole on the other face. Okay, the magnetic flux at the center, and this is very important, magnetic flux at the center of the coil is straight and is perpendicular to the plane. The flux at this particular point is uniform, so we can calculate the magnetic flux density at this particular area by using a certain formula. Okay? Determining the polarity of the coil. What does it mean, determining the polarity? Okay, we want to know which face acts as a north pole and which acts as a south pole. Determining the polarity of the coil. Polarity can be determined by various methods. Okay, in front of you, the face of the loop, where the direction of the current is clockwise, yes, the face behaves as a south pole, S pole. Okay. And the face of the loop, where the direction of the current is anti-clockwise, counterclockwise, behaves as a north pole. Second method, by using the right-hand corkscrew. When a right-handed screw is screwed in the direction of the current is the conventional direction, of course. When a right-handed screw is screwed in the direction of the current, the direction of turning, of fastening, gives the direction of the field at the center of the loop. Third method for determining polarity by using a plotting compass, and it is a practical way. Magnetic flux density at the center of the loop, okay, where the field is uniform, as I said, is given by the relation, by the expression. Yes, magnetic flux density denoted by beta equals permeability Ni over 2R. Let me say it again. Beta equals mu Ni over 2R. Mu stands for permeability of the medium inside the coil, and in the number of turns on the coil, I is the current intensity through the coil, R is the radius of the circular coil. So the formula used, once again, beta equals mu Ni over 2R. If the coil is air-cored, if the medium inside the coil is air, so in this case beta equals 4 pi times 10 to the power of negative 7 Ni over 2R. And now talking about the factors affecting the magnetic flux density at the center of a circular loop. Once again, talking about the factors affecting the magnetic flux density at the center of a circular loop. First factor is the number of turns on the coil. Magnetic flux density is proportional, directly proportional to the number of turns. This happens only when the rest of factors are unchanged. So beta is directly proportional to the number of turns. Second factor, the current intensity passing through the coil, and beta also is directly proportional to the current intensity. when the rest of factors are unchanged. Third factor is the radius of the coil. Beta is inversely proportional to the radius when the rest of factors are unchanged. And finally, the permeability of the core, permeability of the medium inside the core. It differs if the coil is air cored or if it is wound around soft iron or something else. Note, the total magnetic flux at the center of two concentric circular coils. Total flux will be, yes, B1 plus B2 when the currents through the two coils are in the same direction. And of course it is B1 minus B2 when the currents are in opposite directions. And now talking about the field due to a solenoid. The magnetic field produced by, yes, current carrying solenoid. When a current is passed through a solenoid, the magnetic field of the individual turns combine to form a field which is exactly like a long bar magnet. The field inside the solenoid is uniform and it is composed of parallel flux lines. Since it is uniform, so we expect to find a relation, yes, to determine magnetic flux density. Determining the polarity of the solenoid. Polarity can be determined by using one of the following methods. The face of the coil, where the direction of the current is clockwise, behaves as an S-pole, south pole. And the face where the direction is anti-clockwise behaves as a north pole. This is one method. Also, you could use Ampere's right-hand rule. What about it? Imagine that you grasp, yes, a wire at one end of the coil with your right hand, so that some points in the direction of the conventional current, okay, in the direction of the conventional current in one of the turns, then your fingers will point in the direction of the north pole. That's to say, when the thumb of the right hand is placed in the direction of the current in one of the turns, the fingers point in the direction of the north pole. Third method, grasp the coil so that fingers curl around the coil in the direction of the current. Let me say it again. Grasp the coil so that fingers curl around the coil in the direction of the current. The thumb points to the direction of the north pole, to the north pole of the coil. It is shown in front of you. Okay. In this way, we've come to the end of this edition. Until we meet again, my best wishes to you all. Thank you very much.